Let's take a look at this rational function. We're going to look at infinite limits and limits at infinity today. You have x minus 1 over x minus 1. That signifies a whole at 1. And then our even vertical asymptote is any vertical asymptote that has multiplicity, even multiplicity. So something to the power of 2, 4, 6, 8. This is my even vertical asymptote. And what makes that equal to 0? Positive 2. My odd vertical asymptote is, this one has odd multiplicity. It's to the power of 3. So if it's to the power of 1, 3, 5, 7, 9, okay, odd vertical asymptote at x equals 4. What do those even look like, though? Even vertical asymptotes, the behavior approaching the vertical asymptote is the same. Both branches either go up or down. And the odd is they have opposite behavior toward the vertical asymptote. You have seen limits where a limit does not exist at a vertical asymptote. Such non-existent limits can be expressed as infinite limits if the vertical asymptote is even, or if you are finding one-sided limits. We will write the limit as x approaches c of f of x is equal to infinity or is equal to negative infinity for the following. The examples below make use of your knowledge of even, odd, vertical asymptotes, and wholes. The limit as x approaches 2 from the right of x plus 3 over x minus 2. There is some information that we know about this graph. We know we have a vertical asymptote at 2, and we know that it's an odd vertical asymptote because it's to the power of 1. I also know there's a horizontal asymptote at y equals 1. That may be helpful. Okay, so now I'm going to plug in a value that's a little bit to the right of 2, so 2.5. And here's the thing, because there's a horizontal asymptote at 1, meaning the end of this function as it goes further and further away from the origin will end up getting closer and closer to 1, but not crossing it, then we just need to figure out, is a value that I plug in to the right of 2, is that going to give me a positive number, something greater than the horizontal asymptote, or is it going to give me something less than the horizontal asymptote, so that I know, remember, greater than the horizontal asymptote would be approaching infinity, but less than the horizontal asymptote would be approaching negative infinity. That equals 11. So it looks like to the right of 2, we are headed up, 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 and away to infinity. Hey, x is approaching 2 from the left, and it's the same rational function. So that means if this side is going up toward infinity, we already know this is an odd vertical asymptote, so it will be going in the opposite direction toward negative infinity. What about this one? Approaching 1 from the right. We have an even vertical asymptote here. X equals 1 multiplicity 2. So I know that the behavior will be the same, either both going toward infinity or both going toward negative infinity. So I'm going to plug in a value that's a little bit to the right of 1. So 1.5. That ends up giving me negative 2. So it looks like as we approach 1 from the right, we are going toward negative infinity. And what is our horizontal asymptote here, just to be sure that negative 2 truly is headed toward negative infinity? Your horizontal asymptote is the degree of the numerator is less, so your horizontal asymptote is 0. So negative 2 is less than 0. Yeah, we are definitely headed toward negative infinity. Number 4 is the same graph, except they want to know what's happening as we approach 1 from the left. But we know that this is an even vertical asymptote, so we know it's going to be the same as our answer for number 3, which is negative infinity. All right, here we're approaching 2 from either side. Oh, I think I can factor the top. and reduce that. That makes my life easier. Now I'm just finding the limit as x approaches 2 of x plus 2. And at this point, I plug it in. 2 plus 2 is 4. And why was that one so much easier? Because the discontinuity was a whole and reduced rather than a vertical asymptote. If the graph of a function f of x approaches a horizontal asymptote to the left or to the right, f of x is said to have a limit at infinity. If the asymptote is y equals L, then the limit at infinity is L. Okay, so limits at infinity give us end behaviors for graphs of functions. For large values of x, the highest degree terms in the numerator and denominator dominate the other terms and are the only terms that we really need to consider. So to review, we will check out what our horizontal asymptotes are. If the degrees are the same, then you just take leading coefficient over leading coefficient. 5 over 10 is 1/2. So y equals 1/2 is my horizontal asymptote. If the degree is less in the numerator than the degree in the denominator, 0 is your horizontal asymptote. And if the degree in the numerator is greater, you have no horizontal asymptote. So in order to find the following limits, remember that for larger values of x, such as infinity, right, we only care about the terms with the highest degree, okay? The other terms just become so trivial. So really, when I'm taking the limit as x approaches infinity of this rational function, I'm really just taking the limit as x approaches infinity of this little fraction. That actually does reduce, okay? We're still taking the limit as x approaches infinity of 1/2. The limit as x approaches anything of a number is just the number that's there. So 1/2. Oh wait, that makes sense because the horizontal asymptote tells us our end behavior, and so limit approaching infinity is the end of the function and is approaching our end behavior. Interesting. Okay, what about this one? The terms we care about have the highest degree, so we are really just finding the limit as x approaches negative infinity of 5x to the 4th over 10x to the 5th. That also reduces. Limit as x approaches negative infinity of 1 over 2x. So now you plug in negative infinity. There are heavy quotes around plug in, right? You can't actually plug in infinity, but it can help you to imagine what's happening. 2 times negative infinity is basically negative infinity. 1 divided by negative infinity, 1 divided by a massive, massive, massive number is basically 0. So 1 divided by infinity or negative infinity is considered 0. So our limit here is 0. Hey, that was our horizontal asymptote. Ding, ding, ding. I wonder what's going to happen here. So we consider this and this. Okay, so I have the limit as x approaches infinity of 1/2 x. And when I, quote, plug in infinity, 1/2 times infinity is considered infinity. So this one is not approaching a value. This is just simply approaching infinity. It just continually increases. For number 12, here is a note. Make sure you consider the highest degree terms, not the highest degree factors. Okay, so you want it after it has been multiplied out. So here we have one that has not been multiplied out. So it's a little bit more difficult to kind of tell. I want to understand, though, I just want to get the first the first term, the one with highest degree, and I want the highest degree term in the denominator. So I will need to do a little bit of multiplying. I know that this is going to be eventually an x squared. So a 2x times an x squared is a 2x cubed. This will be the leading coefficient of the numerator. You want to check and multiply it all out? Go for it. 3x is being squared, so once this is expanded, that would be 9x squared. And then that will be multiplied by x, so 9x cubed. I've made an error in my notation. Because I did not write the limit symbol here, I could potentially get marked off points for that. Please be careful, even in your own work that's just for yourself. I will rewrite it, limit as x approaches infinity of 2x cubed over 9x cubed, which reduces to be the limit as x approaches infinity of 2 over 9. All right, so the answer here is 2 over 9. Rational functions like those above have at most one horizontal asymptote, so the limit is the same whether x approaches infinity or negative infinity. However, radical functions frequently have two horizontal asymptotes, so you could get possibly a different result approaching positive infinity as you do approaching negative infinity. Again, we're still just most concerned with those terms of higher degree. So this is similar to finding the limit of, I'm going to just kind of cut off the rest of that. I know it feels very weird to just ignore those things like they don't exist. Okay, and that is over x. Is there any other reducing that I could possibly do? Actually, I could take the square root of 4. The square root of 4 is 2. Then we have the square root of x squared over x, and you might be saying, why don't we just square root that x squared? Hey, yeah, we can do that, but we just have to remember that whatever got plugged in to this particular x was for sure resulting in a positive, okay? Because it got squared before it was being square rooted. So the result of this is going to be not just x, but it has to be absolute value x. This 2 could be taken out of the limit because it is just a scalar multiple. And for this one, I'm going to do that. It's not really necessary that you do that. I just want you to really be able to visualize it. This function, we actually know some information about it, that it's part of this piecewise function that tells me when x's are greater than 0, I'm going to get 1 as a result. But that when x's are less than 0, I'm going to get negative 1 as a result. This is something we learned in pre-cal, and you should definitely have it memorized. It also works for x over absolute value x, so regardless of where the absolute value is. Okay, the limit as x approaches infinity. So if I plug in infinity, quote, plug in infinity, infinity is an x value that's greater than 0. So what is my result? It is simply 1. The limit as x approaches infinity of this absolute value, any x's that are greater than 0, the output is always 1. Hey, okay, so 2 times 1 is 2. All right, that's our limit. Let's try this one. Same thing is going on, so really the reducing that we did over here, we do not have to do that again. I just want to get to the step that has the last step that has a limit still in it. So this step is what I'm going to take. 2 times the limit as x approaches negative infinity this time of absolute value x over x. Now, negative infinity is in the other section, right? In the other piece. So you have x is less than 0, your result is -1. This negative infinity is definitely less than 0, so our result is 2 times -1, which is -2.